have discussed what will be in particular the canonical form of an angle relator. And it turns out that with some modifications it will be very close to an angle relator itself, but when we have here in two cases different powers, maybe big powers, so the A that stands here at this end may be different, but for all the rest we will have just a structure of exactly as the angle relator, so except for these layers, this exact underlying here. Here we just have a power of this world, and the A here, the end will be different from the A when the power 1, because here it may happen because B very, very short, and then we will take a power of this and take the normal form, or just the first power, that the A to this will be different, but because in the older position, except for this form, we have B to the power 1 or negative 1, so the rest will have the same combinatorial structure. So what it means that all the results that we discussed about the common position of common small pieces of two angle relators is applicable also to these modified angle relators. It will be very small, because only in two positions we have, in 4 places here we have different structures. It will not seriously change the situation. Now we look in the rank 2. So we have two groups of relators with A from 1 to 2 to the power of 10. The second group will be from 2 to the power of 1 plus 1 to 2 to the power of 20. So we have now two groups of angle relators. Actually, this was the original angle relators. This was modified in this sense, because all the smalls will be considered as they are in canonical in rank 1. So then we take the group G2, it will be F divided by R1 and R2. And then we are going to define the canonical form in rank 2. And actually in all higher, here we have some changes with respect to rank 1, but the higher ranks will be exactly as rank 2. So this is actually the general case. So what happens now? We also consider the lambda semi-canonical word in rank 2. But first, just all the words that we consider are canonical in rank 1. Canonical rank, and they do not, when they are canonical in rank 1 and lambda 0 semi-canonical in rank 2. But rank 2, I mean with respect to this set of modified angle relators in rank 2. Because we know that this structure is almost an angle relator, except these areas. Still we measure this is the A part of it, and then it should not exceed the lambda 0. So we have now this notion. Then we have to look on the one layer map, corresponding one layer map. But also we have to understand that when we take a turn of the board, excuse me, this itself this was a maximal occurrence of a subrelator of rank 2, and this is its complement. But this word itself need not be canonical in rank 1. Because just this point here, these are points where we do not have the canonicity. But then we have to take, not just a complement, the canonical word in rank 1 of this word. But this amounts to consider the triangle of canonical words. Because this is a canonical word, and this is a canonical word, but this is not, it need not be. So then this word should be defined by the triangle. It may be of this one, some region here, and 3 regions here, that will give us, so this how the canonical word for the complement will be distinct from taking just a complement. But all these are what we call domino areas. So they cannot live on many B periods, just on a bounded number of B periods. This is why we have chosen the sequence rho at 1, rho at 2, etc. So these are domino areas. Now, this of course is true for this one, because this is itself an angular relator. But for this we do not know any information about it. It's just a arbitrary word. So in principle, this area domino may be very long. But when it happens to be itself a part of angular relator, then it could not live in more than a bounded number of B periods, say 5 B periods. So this is the way how we construct the one layer diagram. We take some of this occurrences may be substituted by the complement, and then taking the canonical form in rank 1, which amounts to consider the canonical triangles when they occur. Etc. Should be the second time, so everywhere we have a canonical triangle, we may have some deviations from a simple-minded one-layer map. But this is only a minor destruction. But one have to remember this. Okay, now we have this. Then we actually ask the next question at the same time. We would have the certified one-layer map. So then, again, we have our notion of a witness. This will be a pass in this one-layer map, satisfying the corresponding restrictions on the members of the map. And also, we have to do this rescaling. When it is the same kind of the commutator, then the same kind of adjustment we did in the first case, we do here. We just rescale the length by a small factor. So it means that this we count literally, and this becomes very small artificially. And then the argument we used in the Burnside case for the estimating of the domino area is still valid. And of the periodicity, actually we need in 2 places. We need the certified form of the periodic, map is periodic, and when we take the canonical triangle, it displays these properties. So this is just the same, but we have a different way to look on the map. So we have this certified map. It turns out, for the same reason, to be periodic when the original work is periodic. Now here we also take, after the certified map, we take the canonical in the same way. We have a local competition between its neighbors, but then actually what we need, when we choose a certain path, we then have what is the canonical form in rank of one of these paths. So it needs some changes near these places, because each side could be inserted a certain canonical triangle here. So, and then after all, we have what we're comparing, the maximal occurrences of angle relations of the second type. And this we're comparing. We may have it in 8 different ways. When we go this way, or this way, or this way, etc., this is its inverse. So we look at the maximal occurrence of the delta relator of the second rank. If some of them better than others, that is a winner. So we have a winner on my side, but also it may happen that they are equal. And also this may happen only in the entirely symmetric situation. And this is exactly which returns us to this kind of angle relator. Also that these are, in this situation, they are only this what is decisively important. This is the only type of symmetric situation. And this is because when we look on the sequence, the powers of B, this is the only way that we have the same sequence on the other side. Yes, follows from the how is this sequence of signs of B behaved. This is the only situation is symmetric, because this is the next power of 2. So again, we have the same situation. That this could be many of this. Now, here is some new element that was not present before. Because here it may happen that why these are flats of rank 2. Here we have in between, we might have a flat of rank 1. And then again, it's the same B. All of them are commutators with A1, some B or its power, A2 at its power, etc., but depending of the words A1, A2, etc., it could belong to the first group or the second group. So, but they are united in a single composite flat. So both relators from R1 and R2 may appear in the same composite flat. Doesn't matter. Because in any case, these are the parts of the relators. Now, in higher ranks, we will also have another situation in this, with this, not in rank 2, but in higher ranks we may have certain new phenomenon. It could be that here we have something, you see, always here, these are actually in the centralizer of B. I mean, this word is the same word, so this commutes with the power of B, or actually B with B. This word times B is equal to this word times B, modulo of its relators. But it is inevitable because always we have the B commutes, we have A, B, n minus 1 times. It belongs to the commutator of B, because A, B, 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 if we take n times, equal to 1. That means that the n minus 1 commutator commutes with B. And this relator just expresses for variance A. Now, but it may, in this case, the words in the centralizer of B are much longer than B. But it could be a situation that words in the commutator in the centralizer of B could be much shorter than B. How can this happen? Very simple. It could be that B is equal to C D D n minus 1 times, and then B belongs to the centralizer of D. And then D is maybe much shorter than B. So here could be situation, this is a word of these commutators, any product of this, or a product of these words with various C here. So these for the part of the part of the centralizer of B that is much shorter than B. So in general, in an angle group, we have the generalizer of element is generated by the centralizer, is generated by words that are much longer than this, but it could also be generated with words much shorter than it. It's interesting that the shorter part of the centralizer is commutative, because if we have on the B the same structure for different commutators, it could be also C1, D1, etc. Then this will be the same part of two different angle relators.
Because C and C1 are different,
Yeah.
so if they have common part,
Also
it's very
yes,
small, but
yes.
they have very different.
Yes. So it means that the lower part of element of the commutator could be a free abelian group of the arbitrary big rank. But this happens only in very high ranks, but where there is a room for them. In rank 2 there is still no room for them, but in higher ranks it will happen. And then it will result in this kind of very thin parts of the flat. In any case, this is what could happen, but of course the power of B remains constant throughout the whole flat. And then again we have to decide where we so this will be undecided part of it. If it is, and then we have one word entering here, the other word going on the other side. So we have two different ways to cross the whole flat, and then also we have to choose one of these two ways, and then we the same way arrive on the canonical form of a word in rank 2. Again, doing the same. And then, in the same way, of a canonical form in rank 2 of a cyclic word. Taking the big periodic part of it and doing the same procedure. We take the canonical word in rank 2, it turns out it's periodic and outside some periods on the boundaries. Then we have the canonical form in rank 2 of a cyclic word. And in the same way, for a pretzel, with the same thing that we discovered about the powers of B, when the powers of B is big in a certain situation, when is 1 are different, maybe, and when it's 2, 3, some few will go to different situation. So the outcome will be that the canonical form of an angle related in rank, in the higher ranks, modulo rank 2, will also be of the same form. It is not just a angle relator, but certain modification where we have the big powers of B. So this is, so then we can continue doing the same thing. This will be just the same kind of the analysis. So now we're prepared just to repeat this argument in the higher rank, so the rank K. So we assume that everything because but what you prefer? The next will be K plus 1.
K plus 1.
K plus 1. So we've done everything until rank K, assume it's worked, and then we take the next group of relators, which will be RK plus 1. Now, then, with the way we have defined it, so again, in the same way we define lambda semi-canonical, so we take a word, we assume that it is canonical in rank K, and lambda semi-canonical in rank K plus 1. By the way, the canonical in rank K includes this canonical also is all lower ranks, because only these are the ways defined. Now, when we look again at this chart, the corresponding one-layer map, now the canonical triangle now may happen to be of a kind of fractal nature, because we have these areas of rank K, nearby maybe areas after of rank K minus 1, etc., with appropriate domino areas in all lower ranks. So it just, you see, each of them has the same thing, the same structure. Now, but this is not a problem, but just one have to take it into account. Now, when we ask what are the possible flats, now we in general have to take into account that if we fix it some B, then it may be that a part of this is a flat according to this B, corresponding to many different simple flats of different ranks from 1 to K. And also it may be also these areas that are very short coming from the lower part of the centralized B. So this could be the possible structure of the flats for a prescribed B. So then it could, what happens if from other B prime we have the flat in the same place? But assume that B is bigger than B prime. That it means that everything here, and this is avoids parts of angle relators with B and some A's, simultaneously move along this flat. Because this pretzel relators with B appears many times here. So what happens here? So this flat actually should move along this with corresponding with B prime. So B prime should actually commute with this angle relators with this side of it. Because this is some A, this is some B, so this B prime around this should commute with A, commute with B prime, with A and with B. Otherwise, it could not have a flat along the pretzel. And then because this is actually product of many, this is a covering of the pretzel. So just this flat goes many times along this pretzel. So it means that I mean it commutates with some conjugates of A and B of the principle. So what is important to say that here could be many different flats simultaneously for B prime, for B2 prime, etc., existing in the same place. But all of them commutate with each another. So actually what happens here, we might have here a multi-dimensional flat. This is just because this works one glides over the other. So here we may encounter a multi-dimensional flat. This is a new point of view. Because, but then it is the way that one, it means that the presence of the higher rank, just all among them we have the flats of the lower ranks. Okay, in any case. And then again we have the way to take our certified map and to take the canonical map that we have to take decide what sign is better in the competition, in the World Max competition, but what we look on is the instances of the occurrences of the sub-relatives of the highest type, because it ends at certain fixed point, and then we compare them and decide whether one of them is better than the other, with short legs, or they are just equal. As an equal, we have this better situation. So actually then we have exactly the same kind of argument in all higher ranks.
And when you define canonical form for flat, you consider...
Not for a flat.
You consider multi-dimensional one.
I'm only saying, in the situation that all the same angle relator may live throughout flats with different B's. And then necessarily they commute with another. So we have the same angle relator. We have here some B flat around this. We have here also another B prime flat. And then we have another B2 prime, etc. But it means actually this is a bigger one. So this is also considered of the flat itself, its side is a repetition of many types of parts of angle relators. It could be a half or a quarter depending on the same part of the different. And then the next flat rides on the side of this previous angle relation. So they're commuting with them, and then the next is commuting with this and the previous, etc., etc. This is a situation when we might have a multi-dimensional field. But, okay, in any case, just to be aware of it. But now, when we have this canonical form that we actually constructed by the same line of argument and actually the same calculation, now we ask what we will do with it. Then we consider the Van Kampen diagram that will consist of angle relators of very different types. So the Van Kampen diagram that now from various hands. One, two, what's that? Now. Then we take now the series of derived maps. When we have a Van Kampen diagram with ranges of different ranks, so we have the sequence of derived maps. in any case, what we do in each of the situations, we just take, so for example, we have here the ranks from 1 to k. So we take all the regions from 2 to k, and we just the regions of rank 1 are attracted to them according to the distance to these regions of the rank from 2 and just as we have previously done our definition of the derived map. And also we assume the strongest attractors are the regions of rank 2, then of rank 3, etc. And they also are ordered in each rank, so we know who is stronger than who. Now, then we need that in all of these situations there will be the structure of convex layer structure. So in order that we will be able to have the convex layer structure, we need the following two conditions. Here, every region of rank 1, if all its neighbors are only of rank 1, then it needs at least 9 neighbors. If the region of rank is some region of rank k bigger than 1 and more regions of rank 1, then it needs at least 5 regions of rank 1 with one region of the high rank. So these are two conditions that if they are satisfied in the original map, then we're taking the derived map, we will have the convex layer structure in each of the situations. So the volumes of rank 1 in each of them will form convex layers, and then the exact analysis we had previously for the maps with two types of rank will be also here. The first is the short one, and the other was bigger than 1. So then we need, so we will do the same thing now. We will take in the derived map we have regions of type 2 to n, because the one will already here, and then we have these new regions will be derived regions of the first type, first derived maps. Now, we need to check that the same conditions will be satisfied for the first derived map. So here we already take, this will be of rank 2, not just of rank 2, but each of them has an original map of rank 2 and ranks of 1, and then it should be at least 9 regions of this way. And the same here, we have some region of type k, type bigger than 1, and then here we have 1, 2, 3, 4, at least 5 of type modified rank 2. So we just need to have the same condition in order that the next second derived map will have the same properties. So, but here, when it was of the first kind, then this was original angular relators. So we just know that this happens because of the combinatorial properties of the original angular relators. If they are the same time decimal power of 2, negative power of 2, if it is different, a very small epsilon. Now, but here, of course, maybe one needs also gluing the angular relators of the same type if they are glued by quarter. 118, etc. So maybe have here the composite relators of the angle relators of the first rank. Because if their common part is very big, we just consider them as one single region until we come to this. Now, here we already have to consider what happened between them. Between this of second rank, so assume that they are both of the second rank. So it means that they have an original of rank 2, and then we have layers of rank 1. Then we take the transversals, as we do in the case of derived maps. Yes, it's just the same situation. So for everything we said earlier in the Bernstein case, verbally applies here, there is no problem. Now, and then either it will be this way. It means that these original areas are apart from the boundary, and then this will be 4 regions in each of them, so this will be very short. The next situation, that it could be long. This is actually the situation that we need to consider. So, what situation we have here? Assume this is attracting stronger than the second. Here is the second one. And here we have, this is the second. And here we have a series of areas of this of rank 1. Now we know that the transversal will be at most actually only 1, doesn't matter. The transversal here will be give at most 2, also actually only 1, doesn't matter. So we have to look at this maybe a long series of edge of areas of rank 1 between the 2 areas of rank 2. So, what we see? Now, remember that each of these words is canonical in rank 1, because the angular relators are almost angular relators in rank 2 are canonical in rank 1. So it means that if we take this and we try to see what should be its canonical form, the final outcome be that apart from some on the sides, it will be the same thing. Now, and then if we try to determine the same thing from the point of view of the other area, so actually it should be the same thing that apart from a few regions here, the outcome should be this because it's canonical. When we take a canonical word, take a subword and then deciding what will be the canonical form of the subword of a canonical word. So first, because this one layer map, now we know this between them it is short, so the whole should be 1, so this sum is roughly 1 minus something. Now, it could not be that sum is strongly bigger than the other, because then in both competitions it will win. So all of them should be more or less roughly 1/2. 1/2, I mean that less than all constants. So then when we take the so they are belong to the semi-canonical form, of course. Now then we try to take the certified form. For the certified form, we have witnesses. Now, then we know that, for example, this will have a witness, and then this will also be a witness for this, because this is something close to a half, so we can, adding this, it doesn't violate the conditions for a witness. Because this is small, I mean much smaller, we need here lambda 1 or lambda 2. Here we have something like a half, otherwise it wouldn't be both sides here. This couldn't be winner here. So this is close to a half, so it is corresponds to the condition of a witness. So we have a witness here, we have a witness on the other side, so it means that all this except for this will be inside the certified map for this one, and for the symmetric reason inside the certified folder of this. But we moved one region from that. Now, when we look, also move one more region from that, then we look of the competition. Now, we know that in this competition, these are the winners. On the other hand, in these competitions, for the symmetric, these are the winners. The same competition. Because when we move from the two areas, two regions from the end, so we have actually the same one layer map. Now, also, if there would be some part common, then of course it would be the when situation would be. Now, what happens if it would be common? Then, of course, it's complete. Now, if the equation varies, when this is a discrepancy. With discrepancy, it means how both of them could be winners only with this symmetric situation. So now this could not be in this way, because now this set is asymmetric. So this could not be the winner here. Therefore, what happens that either they are together, or there is this a series. Now, if this is a series, it means that this is precisely a flat throughout this. So this side will be exactly the, from this point exactly as this side, because they are both winners. So in this competition, they are winners only this is a symmetric situation, and this is a flat. It means that along this we have a flat, but here it is a lot of each of them. This is a big part of angular relator, so it extends over a big part of the A and B of this. Then it could be extended over the whole of it, because this is a covering of a pretzel, and it goes along the pretzel and it goes along the whole of it. But the same thing for the other side, we don't need it. But what we do now, then we have that around this angular relation, we have this flat. Then we can here glue in this flat in the opposite direction. What happens? This will cancel out in the, like this will go here. And this is the same angular relation, because it is the same on the both sides of the annulus. So in the new map, this one will have a direct meeting with the other angular relator, which is impossible unless it's very small. It turns out that the whole common part will be very small, because two regions here, two regions on the other side, two regions here because we need to take the two steps to the canonical one, to take the certified and then one more to have that area of competitiveness. So we actually see that all of this is short. If it was short, then any area of type 2 must have many neighbors. Otherwise, because we take all of transversions to the east, but each one is very small, that the common number of regions around it should be very big. The same argument works for the second type of problem. This is a k bigger than 2, and this is 2. Excuse me. This is 2 and this is k bigger than 2. Attract here and the same argument works here. Again, what we know that this one could be even a little bigger than a half, because the same way we can gain here the direct meeting, but here the direct meeting of this with the angular later of a higher rank, this could be very big, because it could be here we have CD, etc. So almost a half of this relator could sit in theory, because this higher rank doesn't matter. But not